Okay, so in this second video on continuity, I want to focus on looking at piecewise functions. And example 5 is an example of a piecewise function. And again, thinking back to last semester, even in algebra 2, piecewise functions are just, it could be just a list of 2 functions. This one has 3 functions, and basically defines the behavior of a graph depending what x's you have. So, if x falls in the range of 2 to 5, we're going to behave like this parabola. If x falls in the range of 0 to 2, we're going to behave like this linear function 3x plus 3. And if x lies in the range of 0 to negative 5, we're going to behave like a negative 1, a constant function. So when you graph these, it's good to know the overall behavior of your function, but then you also want to realize that that behavior is only going to apply to particular values of x. So I know x squared plus 5, 1, 2, 3, 4, 5. I know, that's a graph, that's a parabola, right? And I could easily just draw, here it is, x squared plus 5. But I don't want all of that graph. I only want it when x is between 2 and 5. So 2, 3, 4, 5. So it's helpful to know, what are what are the endpoints, right? Because obviously I don't need this. That's not in between 2 through 5, and I could erase all the way up through when it's 2. And notice it's strictly greater than 2. So I'm going to say, 2 squared is 4, and 4 plus 5 is 9. But because it's strictly greater than that value, I'm going to put an open hole or open dot at that point. So that's going to be, didn't necessarily even be that thick, but it's okay, 2, 9. So 2, 9 is where the parabola starts, but because it's strictly strictly greater than 2, I don't fill it in. And then all the way up to 5, and 5 squared is 25, plus 5 is 30. And so way up here, I have another open dot at 5, 30. And again, it's an open dot because I'm not equal to that value, right? It's strictly less than or strictly greater than, depending on how you are reading that inequality. So strictly greater than, those indicate open dots. Now, 3x plus 3. So 3x plus 3, if it were just the entire 3x plus 3 without any worry about domain, I'd go up 3, I'd put an intercept, and I draw a linear function that has a slope of 3. But again, I don't want all of that. I only want from 0 to 2. So again, it's sort of helpful to know, when x is 0, I know that, 0 times 3 is 0, plus 3 is 3. So I know that that whole line, I only need to start at the intercept of 0, 3. Notice I did fill it in because of this less than or equal to, the equal to component. And then when x is 2, 2 times 3 is 6, 6 plus 3 is 9. So I'm going to go all the way up to this point. Now remember how there was that open dot at 2, 9? So it was open on the parabola, but luckily this piece sort of just lined up perfectly and filled that dot. So we filled that removable point of discontinuity. So that's really nice. When I start evaluating limits, it looks like that left and the right both will meet as x approaches 2 from both sides. They'll both meet at the same y value. And then negative 1, if I sketch the graph of negative 1, that's just a constant function at negative 1. So it would be like this. But I don't want all of that line. I only want when x is between negative 5 and 0. And notice 0, it doesn't belong to that graph, so we leave it open because 0 belonged up there. And we go all the way to negative 5. And we do let negative 5 belong because it's an equal to sign in that inequality. So negative 5, negative 1. And then this would be 0, negative 1. So there's my graph of the piecewise function. Now, it's hard to tell this green color here is actually part of a parabola. So there's some curvature to it. And then there's the linear function, and then there's the constant function. Okay, so we've just graphed our first piecewise function. Now, I already mentioned the discontinuity that got filled here, but notice this discontinuity, that's a jump. There's no way to fill that with one particular point. So that is a discontinuity that is non-removable. Now let's evaluate these components. Let's evaluate the limit as x approaches 2 from the right. So we find x equals 2, and I'll just maybe do a nice little highlight of where x equals 2 is at. So x equals 2 is here, and as I approach that value from just the right, I want to know what are the y behaviors, what are the y values. Well, they're getting closer and closer and closer to 9. So we'd say the limit from the right is equal to 9. Okay, the limit as x approaches -1. So as x approaches -1, well, -1, it's kind of an weird, right? It's kind of a weird, I think, value to approach. But -1 is just part of this line right here. As x approaches -1, we consider the values on both sides of -1, and they're getting closer and closer to its same y value, which is a constant value of -1. Okay, now as x approaches 0, now we have something interesting in the graph, because as we approach 0 from the left, right, the limit as x approaches 0 from the left of my function, that's equal to -1, because it's part of, like, as I am approaching from the left, I'm part of that constant function. But if I approach it from the right of my function, then I'm getting the y value of 3, right? And since 3 is not the same thing as -1, we would say that the limit does not exist. And then finally, we have one more. It says the limit as x approaches 5 from the left. So since we're just focusing on the left, we don't know what's happening over here, but we're just focusing on the left, it's okay there's a hole, because the values still are getting closer and closer to that point, which would be 30. So that's what we get for that value there. And then it says, well, when is it continuous? Well, we sort of already talked about that, right? Because it's going to be continuous everywhere, but at 0. So we would say it's continuous from -5 up to 0, union 0 up to 5. Now, technically, I should probably make the -5 also open-ended, simply because we don't know what's happening to the left of that. And for something to be continuous, the left and the right have to match up. Now, some textbooks distinguish that as, well, it's continuous from its one-sided limit. So the good thing about the AP exam is they're not really as focused on the subtle details like that, as opposed to this jump. Like, what makes 0 discontinuous? Oh, it's a jump. Okay, so speaking of jumping, I'm going to allow you to do number 6 as part of your homework exercise, but I just wanted to revisit number 7 and honestly sort of change the problem slightly from what in your book. Let's not approach infinity, but let's think about the limit as x approaches -1 from the right, and then also from the left. So let's make it into 2 components, because I want to analyze this problem approaching -1, because -1, that's our point of discontinuity, or that's our value of discontinuity. It's not a point; it's actually an asymptote, because I can't cross that out. Right? There's no value that would factor in the numerator to cross that out. So I definitely know there's an asymptote at x equals -1. And if I think about what would this graph look like, if you pick things that are bigger than -1, like 0 or half or whatever, it stays positive. So I know that from this side, we approach the asymptote going straight up. But then on this side, if you pick things that are left of -1, it makes that function negative. So we get that. So what I wanted to illustrate here is that, so as you approach -1 from the right, so again, -1 from the right, so from this side going this way, right? So we don't approach a particular value, but it does increase without bound. So we could say its limit is infinity. Even though we never get there, it still gives us the behavior of the graph. And then hopefully you can see as we approach -1 from the left, so from this side, things are decreasing without bound. So we say that limit is negative infinity. So just a few more examples of continuity, piecewise functions, and looking at that. So try the homework that's posted on the slide deck. and see how that goes. And then we'll kind of bring some closure to this introduction to calculus on Friday's lesson.